So this presentation is going to be about sequence-to-sequence model. So we will show this new architecture that is going to give us more flexibility so that it will allow us to solve problems such as, for example, machine translation. So the plan is the following. So we will actually start with a recap on the first presentation to see the most important points from that presentation, also because we will use some of these in this presentation as well. We will then introduce the sequence-to-sequence models. And the idea there is, as usual, we will look at which kind of problem we are trying to solve. Then we will introduce the models, and we will run the models on an example, step by step, to really understand how they work. We will also see that there is one issue with this model that we will try to solve in point number 3, so the attention, where we will introduce the attention mechanism. And we will see that the idea of attention is really a clever and key idea in this field. And it will definitely improve the result, and it will definitely improve the flow of information in the sequence-to-sequence model. And in the next step, in the next point, the transformer, we will talk about this architecture, which is a very important architecture in this field. It is completely based on the idea of attention. And today, most of the state-of-the-art system in natural language processing, they are still based on the idea that comes from the paper that introduced the transformer architecture. And at the end, I will show some libraries and references. OK, so I'll start with the recap. So now you should be familiar with this slide. So here you see the RNN. In particular, you see on the left what we call the general representation for the RNN. You see on the right the unfolded representation of the RNN over the input sequence to generate the output sequence. And we can, I would like to highlight the two very important points of this architecture. First one, it will run over the elements of the input sequence one at a time. So it will not work on the full sequence altogether. And while doing that, it will keep an internal state. And we saw that this internal state, the RNN is trying to capture the relevant information that have been seen so far in the sequence so that it can be used in the current step or in the future step. Another point that was also important, the parameters of the RNN, they are shared over time. Like here you see the VWU, and if you look at the unfolded representation on the right, they are always the same parameter at every time step. And then we show how to train RNN. So this was somehow complex because we showed how to backpropagate with this on this computational graph. And we saw that it's the usual deep learning backpropagation, but with two differences. The first one is that we now have more than one output. In this example, you see 3 outputs. And that means that we end up with more than one error. In this case, we have 3 errors. We show how to solve this. We basically compute the gradient of all of these errors separately with respect to the parameters. And then we sum them at the end. So it's like a for loop. And that was the first distinguished point of RNN. Second point, even if we fix on just one error, the parameter that I'm trying to compute the gradient for maybe has been used more than once. And this is because, as we mentioned before, we are sharing the parameter over time. And in this case, what we need to do is, again, to compute all these gradients separately and to sum them at the end. So that's why I said that in the end, it's like having 2 for loops, one going over the errors and the other one going over the places where the parameter has been used in this computational graph. And at the end, if we sum everything together, we have the correct gradient, and now we have a correct backpropagation. But we saw that in doing this backpropagation, we may have problem if we have many, many elements in the sequence. And this was mainly due to the fact that in order to backpropagate in the past, I need to pass through all these internal state. And that basically results in a long chain of computation where every element is a gradient of the internal state with respect to the previous one. And we saw that this was leading to two problems, exploding gradient and vanishing gradient. We had a solution for the exploding gradient. We can just cap the gradient, but we don't have a solution for the vanishing gradient. And because of this, we introduce another architecture, the long short-term memory, so the LSTM. And we saw that there are two key intuitions in this architecture. The first one is that we have this memory cell. So instead of having just one lane for the information to flow, like before we only had the internal state, now we also have this memory cell that hopefully will specialize in capturing long-term dependencies, so in allowing the information to flow for many steps in the future. And also, we added the intuition of the gating mechanism. So we would like to selectively control the flow of information. And to do that, we use these gates. So a gate is basically just this element that can be between 0 and 1, and is telling my model how much the information should flow in that particular point. And we saw that the LSTM, they have three gates, two to control the input and the output, and one that we call the forget gate to control how much information should go from one step to the next step. And we also saw at the end how to make this architecture able to approximate even more complex functions. So on the left, in this presentation, you see how to make this architecture more deep, which basically means we can stack layers of RNN on top of each other. It's done easily just by the internal state of one RNN becomes the input of the next RNN, so here. And in this example, I only have 2 layers, but I can stack many, and today we usually have 12, 24 layers. The other way to make this, the RNN more effective is to use this bidirectional technique. So in some problems, it is not only important to look at the information that comes from the past in my sequence, but also the information that comes from the future. And in the RNN that we show in the first presentation, we were always going left to right. So we are only able to look at the past. In this slide on the right, we can see instead how to also exploit information from the future, because we are using 2 different RNN. One goes left to right, and one goes right to left. And then we combine them together. We can somehow merge the output. And by doing that, when we are at the given time step, now we are able to look at the past, thanks to the left to right RNN, and at the future, thanks to the right to left RNN.